All right, so welcome everyone to today's presentation by Causley and D-Zone, where we'll cover rethinking reliability for distributed systems. I'm Ben Yamini, and I lead product management at Causley, and I'm going to act as your host for today. In this session today, we're going to explore why more observability data doesn't always lead to better insights, especially when it comes to complex microservices environments. You're going to learn how causal reasoning goes beyond correlation to deliver true system understanding, helping teams move towards autonomous, self-healing systems. And I'm super excited to be joined today by Andrew Sara. He's a co-founder of Causley. Prior to his current role, Andrew served as the vice president of advanced engineering at Turbonomic, where I had the pleasure of first working with Andrew more than a decade ago. And he's also had leadership positions in technology organization at Goldman Sachs. And it's great to have you here today, Andrew.
Hi, Ben. Thank you.
Yeah. All right. So let's get started. So, Andrew, one key question maybe to get everybody started here is why is it harder now than ever before to achieve reliability? Why do we see people struggle with this?
So this has always been hard. If I think back some more than 20 years ago at Goldman Sachs, working on a trading floor, it was really, difficult to keep applications healthy and services assured all the time. One of the ways that you could tell that things were not working, that monitors were thrown at you, and that is not a happy place to be. And this is before, flat panels. These were CRTs, so especially harder to dodge. Now, things have gotten even harder over the last 20 years, partially because back then, if you wanted to run an application, you had to, buy some servers and rack them and then install the software. Now with cloud, you could just on the fly spin things up. With containerized microservices, you could, instead of booting a VM, now you could bring up, scale out services in a matter of seconds instead of minutes. And as you're breaking things up into smaller microservices, you're using an AI coding assistant. You could develop software faster. You could replace these components. So you really are able to deliver to the needs of the business, to be able to scale faster, innovate faster, combine together different building blocks to deliver your applications. But all of this is resulting in an increased operational complexity for people to keep in their head, what is the services that are depending on each other, how they are interacting with each other. And when something is not working, what could be the possible reason for this is becoming really hard. So it basically, people are losing control, even though they are delivering services faster.
Yeah, and then maybe as a follow-up, I think what we've seen is that to address this, people are instrumenting everything, right? So they're collecting a lot of data, but why doesn't that help, right? Why is adding all this data and all this instrumentation doesn't help folks fully solve this problem?
So instrumentation is important. You do want to be able to observe things in your environment, but simply observing it doesn't mean that you actually understand the behavior of the system. And the point of being on control of your application is the understanding of how these things are working together. So as you are scaling services, as you are combining these services, the dependencies between these things change. It is not only the volume of data that you can collect and most of people are collecting or changing, but the cardinality of these data changes as different things are dependent. So for example, I can spin up a set of container, scale it down, scale it back up. Now I have a new set of containers. So now I am collecting a new set of data that is now part of my dependencies. and now I need to be able to reason about those new set of containers are being a dependency for this service that I'm delivering to customers. So this continuous shifting and scaling of dependencies makes it increasingly more difficult, even if you are collecting more data, even if every one of those things are independently and individually observed. Another thing that makes it really hard is that even if every piece of your microservice, your front end, your back end, your middleware, your managed services are being observed, they are often developed, deployed, and operated by adjacent teams. And simply observing each piece of it, it's not that they are not in one system, they are not actually viewed by the same people, which makes it, again, really difficult to see how these interactions are happening between, or to put it simply, understanding how the system behaves at large from the perspective of how it is being consumed by a user. Just monitoring a single component, scaling a single component is not sufficient to make sure that what you're providing is a performant and reliable service, even if every single component is observed, monitored, collected.
And maybe just to follow up and to give the folks that are joining us today a little more understanding, can you maybe think of an example? I know we talked to a ton of customers, and for years or decades you've been looking at this problem. Maybe share a recent example where we've seen somebody who has invested, an organization that's really invested into observability. Maybe they've standardized on a observability platform, and they're still struggling with this.
Yeah. So in fact, in terms of our current business, Causally, we are primarily working with customers who are very mature, both in terms of the scale at their services, as well as the instrumentation and the availability of all the observed data in their services. So, for example, one of the recent conversations we had was with a company that has a fairly complex environment deployed across multiple states, and they take advantage of both. I mean, all of their services are microservices. They're running in Kubernetes. They're running in a cloud. Anything can scale up or down, and it does. They rely on database services. They also rely on asynchronous messaging, Kafka in this case, to communicate between the components. Each one of those things are monitored. They are collected, distributed, tracing across all of their microservices. They are monitoring their managed Kafka service. They are monitoring their managed database services. And when there is a major business event and something is not functioning, they still spend hours and sometimes days figuring out which part of their system is responsible for that service degradation and what is the actual problem. The combination of these services, not just synchronously communicating with each other, and it's not necessarily a single pipeline of one service calls the other service calls the third service, and that's it. There is this mesh of data flowing through their system, makes it really difficult for them to figure out where and what the problem is. Even though everything is instrumented, they've got really well organized distributed tracing, semantic conventions collected into, in this case, a super nice Grafana stack with all of the dashboards exposing all of this information, yet struggling to have an understanding of the actual behavior of their systems.
Got it. Thank you. All right. So if if observability is not the answer, or more data, what is a way to kind of make software understand itself, or so maybe help our listeners understand what we mean by that?
Yeah, so both just thinking about our own software that we're operating, as well as especially the customers that we're working on, even for the most experienced architects who are responsible for day one of the software that they're delivering, it is really hard to hold in their head the components, the dependencies, especially the runtime behavior of the system that they designed, they implemented, and rolled into production, and especially under pressure when there is a service degradation, to try to put together in their head, if these are the things that I'm observing, how those things can cause, or what those things can be caused by. So we believe that the answer to this question is that this problem has to be solved in software. You can't purely rely on humans continuing to have their whole system architecture, their whole system behavior in their head, especially with what we mentioned earlier, with the continuous agility and scaling and ongoing innovation that goes into your software, the changing dependencies in your software, and given the volume of data. So we believe that to understand the behavior of the system, you need to understand causality, but that causality has to exist in software. It has to be captured in software. It has to be analyzed in software so that the behavior of the system is understood by software rather than data being exposed to people, even experienced people, trying to create that understanding. So what we mean by this is not just discovering the entities, discovering the topological relationship between those entities, but to be able to reason about how these systems can degrade, how these systems can fail, and how the different failures can propagate and manifest themselves through those relationships. So if you think about, there is a knowledge base, a knowledge graph of my topological relationship in the system, there is another graph that represents the causal relationships that is actually a different graph for the different type of failures. And that causal graph, most of the time, gets created in people's head today, even if they can look at the topological graph. So where we're going with this is software creating that causal graph, of course, by discovering the topology, but ultimately creating that causal graph and searching that causal graph instead of a human saying it like, well, I think this could be this thing, let me reboot this. Oh, I think this could be this other thing, let me reboot that. Taking the human out of that hypothesis creation / validation process, use software to actually not only to be able to create these causal graphs, but to be able to, in real time, in runtime, to be able to search those causal graphs and present an actionable result that can be automatically orchestrated, either by an orchestration system or maybe by another AI agent, to recover the service without relying on people in the middle to do this. So effectively what you're surfacing is not the topology, it is not the anomaly, but it is the actual intervention that you have to take to remediate the service or to be able to prevent a degradation of the service and continuously keep the application healthy, assure the reliability of the services, which is what we mean by control.
Got it. And then maybe I think you started to hit on these points here, but maybe to kind of make sure folks we're all following along. If we kind of rethink of a reliability reimagine, maybe walk folks, what does that mean?
Yeah. So yeah, I probably jumped ahead a little bit, but that's okay. I guess it's the individual components are possibly understood by the people who develop them. Like I can understand my single microservice. What we mean by reliability is to be able to cross these microservice boundaries, cross these technology boundaries and often organizational boundaries, and to be able to understand the behavior of the whole system is to be able to define from the perspective of how this service is being delivered to your customers what normal looks like. So instead of trying to start bottom up and reacting to the individual anomalies, individual alerts in the various microservices, to start with, like, given these are the services that I'm delivering, this is how those services are being consumed, this is what normal looks like. If that service degrades in the context of how the customers are experiencing and consuming that service, infer what is the root cause across the multiple components, multiple technology stacks, or multiple organizations, and basically pointing out what do you need to do to assure the reliability of that service, rather than everybody getting on a Zoom and like troubleshooting for 15 hours, or finger pointing and pulling other people into a incident response call. Effectively reduce, I mean, you still have to manage an incident. Things are going to break. I wish they didn't, but they do. But significantly reduce both the mental burden as well as the actual time spent in this incident process, from the point where you are able to observe some of the degradations to the point where you know that this is where I need to intervene, and effectively, if you're able to automatically intervene, then even basically create a self-healing system that is effectively a closed loop process that is not only able to infer the root cause, but automatically recover, remediate, or prevent further degradation of that service. And of course, doing this on an ongoing basis, so that it's not like I get an alert and now I have to, react to it. It is a continuous, ongoing operation of your services done by software, rather than pulling in experts and people in the middle of an incident.
Got it. Yeah, I certainly remember being previously to Causely, I was responsible for a distributed service, and those days when I would get called into a war room and then have to later on write a postmortem were my least favorite days. But leading to your point, what if we could prevent outages in the first place, right? Instead of we can certainly hope that people can shorten the time it takes them to fix, but what about prevention?
So a software-based causal analysis of a causal understanding of your system behavior not only allows you to react to a incident as it is developing, as you start to observe the service degradations and then more and more things are failing in the environment, but you could actually take advantage of this causal understanding of your software system, even during a development process, as you're moving into production, even before anything actually is degraded or anything breaks. So using software to point out, like, you have a single point of failure here. Nothing has failed, but because I understand that these are the ways that my database can fail, these are the ways that my Kafka broker can be, running out of memory. You could actually analyze and possibly improve, or at least assess, what are the things that you want to invest time in, so that you don't have an incident 2 weeks from now. One of the interesting aspects of modern application deployments and platforms is the ability to be able to, a single microservice crashed, it will restart. Something gets killed because it runs out of memory, it gets automatically restarted. But those gray failures are both causing occasional service degradations, but if they are not addressed, then eventually they will lead to a major incident. To be able to understand how those things that can happen in your environment can impact your services, to have this causal understanding of not just this individual component, but this individual component in the context of the overall system behavior can impact your customer experience. can help your development team to focus on burning down their tech debt, avoiding problems, evolving their architecture, not after you have done this painful post-mortem as a reaction to a major incident, but preventing that major incident, but focused on how those services are dependent and can be possibly degraded in the future based on things that you might already observe or might not even have yet observed in your environment. So we are basically proposing software that can not only react to the incident, but prevent an incident, help you to drive your development process by both your pre-prod and your production environments, runtime behavioral understanding.
Got it. Yeah, so that sounds amazing. It also sounds like could potentially be very maybe daunting for some of our customers. Where do you see? How do people start? Where do you see customers start?
So we're really specifically in the context of Causal, we are trying to make this as easy to get started as possible. Part of this is that while I am working with customers who are mature, who are running applications at a large scale, and they have fairly broad instrumentation of not just collecting logs and metrics, but also distributed tracing across their environment, there are still places where things are not instrumented or the instrumentation is out of date. So as part of our software, we are taking advantage of open source software in general, not exclusively, but we're a huge proponent of open telemetry, semantic conventions that are providing consistency, a vendor-independent consistency on how your applications are being instrumented, and also auto-instrumentation that can basically create the necessary observable signal to be able to reason and infer the root cause in your bespoke environment. So what we mean by light deployment is instantly to be able to take advantage of instrumentation that you have, complement that where that's necessary in a matter of minutes without you actually having to change your code, without you having to redeploy your software, actually without even having to restart your software. And also within a matter of seconds and a minute to be able to get real-time insights into the current state of your system, and to even to be able to ask questions without waiting for something to break on what can happen in my environment and how a particular root cause that might happen would impact my customers' services. So as opposed to waiting for an incident to happen and then train some data based on an incident, be able to deploy and instantly understand the causal behavior of your whole system. And of course, instantly, and hopefully it doesn't happen in the next hour or maybe not anytime soon, if there is actually a customer impacting incident, to be able to immediately identify it rather than waiting for it to, be learned and then trained and then eventually the next time catching it. So the instant benefit is to be able to deploy in minutes, to be able to understand the reason about the behavior of your system in minutes, and instantly be able to identify any customer impacting root cause that you either want to resolve or put into your sprint plan, which kind of moves on to the next point of, okay, now I am significantly reducing the impact of an incident. Now I can take this and not just after an incident, even before an incident, expand the use of such a capability as make it part of the development team's process, to be able to say that, like, well, these are the 5 top most important things that can cause service degradation. Take the first 2 or whatever fits into your next sprint, and improve the architecture, improve the reliability of those highly dependent microservices, highly dependent components. And then, of course, start with any particular part of your application stack, but to be able to easily expand into other components of your application to the extent that you have control over and effectively get an even broader understanding of the overall system behavior. Some of this could be like a shared authentication service that is used by two different business applications running in your environment, or just simply, a front-end service that now relies on some back-end service, and effectively broaden the benefits to the multiple teams that are operating maybe the parallel or interdependent parts of your digital service.
All right, great. So maybe we can transition to showing folks what this looks like in Causely.
Okay, so basically, as we mentioned earlier, Causely can instantly deploy and discover all of the building blocks of your application, all the way from the data flow through HTTP paths, RPC methods, asynchronous messaging topics, database tables, to the underlying containers and orchestration platforms that are running it. But instead of one manually trying to look at, why is there a consumer lag, why is there high CPU utilization in the environment, and reacting to individual alerts, to be able to instantly get an actionable insight from what are the root cause or root causes that are impacting my services. What action do I need to take, rather than investigating the alerts one by one? In this case, we actually have 4 active root causes in our little demo environment, and one can drill into, instead of multiple teams looking at how the position service and the front end service is SLO being degraded. The Causely has identified that the root cause of these service degradations is actually a connection problem on the Postgres service. So the team that's responsible for the Postgres configuration, or maybe the automation that manages the Postgres database, can instantly take an action and resolve the root cause of this problem, instead of troubleshooting the individual alerts. Because otherwise, what we are also highlighting is the causal relationship between the specific identified root cause and how this root cause from the Postgres database is propagating to the various services, to the order service, to the front-end service, or the position service accessing the Postgres database. Each one of these individual anomalies could have been sent to different teams as an alert. Instead of looking at these alerts, we're instantly identifying where and what the root cause is, and what actions do you need to take to be able to remediate this root cause and effectively recover the service. And of course, we are doing this broadly on any type of application infrastructure, both in terms of synchronous communication between the applications. Like in this case, this portfolio service is not being able to handle the load. It's congested, and the fact that it's congested is causing an SLO violation of multiple services. Of course, the answer to this is to scale this service out, but to understand how Causely identify this service, we are again automatically creating a causal relationship between the identified root cause and all the anomalies that have been identified, effectively automatically notifying or orchestrating the resolution of this root cause, in this case in the portfolio service. So in general, we are basically following the same pattern for database, for synchronous communications, for asynchronous communications, or any combination of those things that make up your application, of taking advantage of the observability tools that you have, the instrumentation that you have, or complementing it with open source software where necessary, inferring the root cause and then feeding that inferred root cause into an automated recovery system or maybe into a notification system so the right team can either automatically or manually take the right action and quickly recover the service, with the ability to also to be able to look at what are the other non-service impacting things that I want to improve in the next sprint. Like, for example, I've got some bad mutex locking in my application, which is causing delays in the way that I am consuming messages from various topics in my microservice. But instead of chasing the individual consumer lag on the individual consumer groups from the variety of microservices, we could tie it back to this is the application, and the team that's responsible for application needs to improve the way that this application handles multi-threading and the locking of the data structures across those multi-threads, and not have to bother the rest of the things. Now, this is not service impacting, so this may be something that people will say like, well, that's really nice that you understood this. I'll pick this up on Monday. But instead of the 15 alerts, I know what to pick up. I know it's important because it has the potential of propagating and impacting my services in the future. So effectively, your development process becomes focused on your services, on your customers, and what do you need to do specifically to be able to prevent an incident going forward.
Thank you, Indra, for that in-product walkthrough. And to kind of maybe close us out here, we are very eager to hear about your challenges. Hopefully today you've learned about some of the challenges we see our customers and folks in the industry have with distributed, complex microservices environments, and how observability is important but insufficient to overcome those challenges. If you're interested in talking with us, feel free to reach out. There's also a completely risk-free and very easy way to try out Causally in your environment, or even in our sandbox if you're not ready to deploy yet. With that, thank you, Indra. Maybe I'll hand it off to you if you've got any other thoughts or anything else you want to share.
Yeah, I think that it is an amazing opportunity to continue to work with customers. So I'm really looking forward to engage with more people, especially as they are operating large, complexes with microservices, and to be able to prove that this problem can be solved in software. You don't have to get page 2 a.m. in the morning and then, wake up and join a Zoom call for the next 6 hours. We can actually make people's life better. I believe that we can help you to continue to improve your application architecture, build better software, and deliver services as fast as it is promised by all the agile methodology, but without all the risks and the not all the risks, but most of the risks to impacting your customers and degrading your services. And we want to continue to learn more on how we could apply this platform to solve not only the things that we are already solving, but as new technologies are being evolved, agentic AI experiences are making this even more exciting and more complicated, how we could continue to not only improve the user experience of people consuming services, businesses consuming services, agent consuming services, and effectively deliver a reliable, scalable digital service for any one particular company's customers.
That's great. Thank you, Indra, once again. And if you're interested in Causally, please go to causally.ai or causally.ai/try. There's a link right there to engage directly with Causally in your environment, and we'd love to hear your feedback. Thanks again.